shaft is a rotating member, usually of circular cross-section, which transmits power and rotational motion. Machine elements such as gears, pulleys, flywheels, clutches, and sprockets are mounted on the shaft and are used to transmit power from the driving device through the machine. Press-fit keys, dowels, pins, and splines are used to attach these machine elements to the shaft. Shaft rotates on a rolling contact bearing or bushed bearing. Various types of retaining rings, truss bearings, grooves, and steps in the shaft are used to take up axial loads and locate the rotating elements. Coupling are used to transmit power from the drive shaft to the driven shaft. A hydroelectric turbine, also known as water turbine, is a rotary machine that converts kinetic energy and potential energy of water into mechanical work. So it was developed in 19th century and were widely used for industrial power prior to electric grids. Now they are mostly used for electrical power generation. Water turbines are mostly found in dams to generate electric power of water potential energy.
So we move to the transmission shaft, which is in hydrokinetic turbines. Transmission shaft is the first component to receive the power generated at the turbine. Role of transmission shaft in the hydrokinetic turbine is to transmit the torque generated at the turbine blade to the generator. This done using mechanical power transmission components such as chain, gears, sprockets, belts and pulleys, and eggs. The uncertainties involved in design process of a transmission shaft include uncertainty in loading conditions, modeling uncertainties, and physical uncertainties. It is necessary to take into consideration all these uncertainties to design a reliable shaft.
Now I would like to talk about what is our material of hydroelectric turbine shaft. The material selected for the shaft is cast steel. This is because the turbine is always rotating with high revolution per minute. Since it is located at the bottom of the reservoir, so it endures a big water pressure continually. Hence, the shafts are constantly under fatigue loads and high stresses. Thus, a tough and fatigue-resistant material is needed for the shaft. Therefore, cast steel is selected due to its high strength and toughness.
Explain my calculation about my shaft. So as we can see right here, this is my free body diagram and this will be my roughly sketched shaft. So my force assumption right here will be around 127.512 Newton, as it is my assumed force from the waterfall that could exert to my turbine. As you can see right here, this is the shear moment diagram for my shaft based on my own calculation and all of the resistance force. Okay, next. Based on the shear moment diagram, I've gotten all the forces. So after that, I will try to use those forces and find stresses, especially bending and torsional stresses. And this is the force equivalence for my shaft. As you can see from the force equivalent, I've constructed a Mohr circle so that we are very clear about the shaft analysis. Now for the stress analysis, I've used, for my safety factor analysis, I've used equation from moment equivalent and torque equivalent equation so that I could find the safety factor afterwards. So right now, my safety factor is at 29.586 for bending and 29.76 for torsion. Okay, this means that my shaft is safe because my safety factor is much greater than.
Next, we move to von Mises stress. As we can see here, the color contour. The bottom value, it shows that the material is under the yield region. As it's going up to the maximum value, it shows that the material has tendency to be fractured. As we put the force here at the arrow, 1 to 7.512 Newton, it shows only this part has different color contour. It means that only this part has tendency to be fractured, while others in the blue color, it's still under the yield region.